Hello everyone, I'm Jimmy Koppel, here to tell you some very exciting work we have. It's joint work with Nadia and her student Zheng, my advisor Armando Solar-Lezama, and our research programmer Edsko Vries. So, in synthesis, there's been a lot of work on representing program spaces. I want to write down 10 to the 100 programs, and then find the one that satisfies my goals. It's a needle in a haystack. Our twist is putting extra constraints on these program spaces. Before I get to explaining what that means, I want to show what we can do with this. 2.5 years ago in Koppel, my co-authors created a tool called Hoogle+, which is type-directed synthesis for Haskell. So what it is you give it a type that says something like, I'm going to take a function and an argument and apply it n times the argument. It thinks, and it gives you the program for that. So we did this with an S&T encoding in Koppel. With the new technique presented today, we created a better version called Hectare. How much better? Well, clearly it does more in less time. This is the comparison of how long the old version takes versus the new one. Top left means Hectare, our new thing, is really fast, and Hoogle Plus is very slow. You can see it's all very much to the left, 8 times faster on average. Let's zoom in a little bit. You can see just how compact it is. And there are even a couple things. Hoogle Plus times after 5 minutes, and Hectare does it in another 3 seconds. But of course, not only does it do the same stuff faster, it also does more. Several times more benchmarks from another data set, which has more high-order functions. And my favorite comparison, it does all this using 1/10 as much code. So how do we get such amazing results with 1/10 as much code? And the answer is that we have a new kind of data structure for representing these spaces, a new kind of constraint solver. It happens to be extremely good at this kind of problem. I bring to you ECTAs, Equality Constrained Tree Automata. So what are these equality constrained tree automata? So let's go back to the problem of program spaces. A technique that's pretty popular for representing these large pieces of programs is E-graphs, and they work like this. Big insight. I want to have a bunch of additions, 10,000 things to the left, 10,000 choices to the right. Together represents 100 million possible programs. So a big circle is an OR. Have one choice, the plus. The 2 edges into our ands. Going to select some arguments from this bubble up here. And they can both be X. But we add new things to that. Say add a Y, now add 4 possibilities, add a third thing. Now this data structure here is representing 9 possible programs. And if we keep going like this, and we add more nodes, we can see in a small amount of space, I can represent an exponentially large number of programs. I think that's great. We've done amazing stuff with E-graphs. But now I'm going to add a constraint. I have a rewrite rule. A plus A rewrites to 2 times A. And I want to represent all the programs that match this. This is a nonlinear pattern. So fewer programs than I had before, strict subset. So we can't use the same representation because that lives in things like X plus Y. I don't want X plus Y, I want X plus X. So with E-graphs, you have to write it down like this. And this is not so compact anymore. So in fact, in one of the first works 20 years ago on these kinds of program spaces, another thing called vertex space algebra was very similar. They wrote that it was a solution to representing huge numbers of programs by exploiting the power of independent choice. But he went dependent choice. That's an open problem. And today I present to you the solution. So let's go back to the domain of type-safe programs. So here I have 4 programs. And I'm going to introduce you, let's turn these trees. So another way of doing it, which we'll be building on, is tree automata. So what is a tree automaton? These circles, the states, are ORs again. At the top, we have one choice, the application $node. It's for the function, I have 2 choices f and g. I call it the unary state. The squares are transitions. Those are ands. So what does it represent? Here's an accepting run. I made one choice for each of the circles, and it represents fx, f applied to x. Now, let's add some constraints. I'm going to type everything. So I need to add some more information to this. Every single variable here is going to be given a child, which is its type. And I need my function argument type to line up with the actual arguments. And these are the equality constraints in equality constraint tree automata. The way you read this is, it's a path. You see that $sign has 2 children called function arguments. The arguments, the function, after I made the choice, they'll have targ and tret children. So the return type of the function has to match up the type of the argument. That's all this path constraint says. And so now this only accepts a well-typed thing like fx, but does not accept fy because that constraint is not satisfied. And with the constraint language, we can do fancier stuff. So let's add polymorphism. I'm creating any type. Let's say there are only 3 types in my universe, int, bool, and char. And h now is type any to any, but I need them to be the same any, int, not int to bool. So we add another constraint onto this h, saying there's 2 any's for input and output types have to line up. Now I want more than 3 types in the universe. I want infinitely many types in the universe. We just add some cycles. Now this any node represents lists and functions. Anything you build out of these type constructors, entire language of types, base types, int and bool. Now, going to represent the map function. And I just use this any node from here inside the type of the map function. Now we have function from A to B to list A to list to B. I add some more constraints, say the 2 A's have to be the same any and the 2 B's have to be the same any. And now I've shown that I can represent this entire space of well-typed polymorphic terms with the ECTA. So why do we care? Well, we care because we can actually get these terms that are type safe very fast out of this. So, in fact, these implementations showed you earlier of our tool, all it is, it builds an ECTA that represents the space of things you want, and it hits give me the satisfying terms. But doing that's actually not so trivial. So we'll look at this ECTA again. See, it represents a lot of invalid things. So can't instantiate h from int to bool because it violates the constraint on h. This one, h can be bool to bool, it can apply to x, violate a different constraint. But this one, h applies to x, h into int satisfies. So for this ECTA, only 20% of the runs satisfy the constraints. So we need some clever way to find all the satisfying things very quickly, because as it grows, it's going to be very, very few that satisfy the constraints. And so I actually am going to spend a few minutes explain our enumeration algorithm, because it's a little clever, but also because it's at the heart of how we get such great performance results. So the idea is that we're going to resolve the constraints lazily. So I make a choice. I say, on the root node, I'm going to pick $, because it's the only choice. But it has a constraint on its types, but I don't know what this type to be at, so I'm going to decide it later. Split into 2 subproblems, but both sides are going to have a type that lines up something. So let's pick the next choice for my function, h for g. I'll just pick h. And again, I'm looking. So if constraints merge, with my local constraints on each transition are turned into a global constraint system about all the types in this entire program that must be the same. And I push down again. So now I need to choose what the input type is, but I'm going to defer that because I have to make the same choice somewhere else. And you make the choice of what the output type is, I'm going to defer that. So now I know I'm going to make the same choice for both sides when I make it. Now go to the other side, look at x, and lo and behold, it tells us that this type that I'm going to make a choice in all 3 places has to be int. And the magic of automata intersection just tells me I found the satisfying term without backtracking. The only thing can make out of h. So I go back to the top, choose f this time. Once again, similarly, we're going to find the only use of f in a well-typed term without backtracking. And so this fast enumeration is a secret to how we get the great results I showed you earlier in so very little code. So that's Hectare. It's now a GHC plugin. You can download and try, thanks to my collaborator Matthias, who is somewhere in this audience. So we have this very new fancy data structure that lets you generate Haskell programs. Well, we can do more. So all you need to do is just set up ECTA and run it. And there are more domains we can apply it. So, as a little toy, just showing you just how powerful constraints can be. It's actually pretty simple to encode sat into ECTA. But something we're excited about is that E-graphs are very bad at sharing space between two terms, which kind of differ at place in the middle, things that can be anti-unified. They're very bad with binders. With ECTAs, we essentially have a form of what's called reverse de Brown notation built in. So we think can actually do a lot of cool applications of binders. Another domain that we've actually done, paper we have submission with Matthias and a former MIT student Diego, is so there's a problem where I give you some functions and you want to find laws in these functions to use in property-based testing. And there's previous work where you just give it 3 functions, it'll find a bunch of laws kind of slowly, and thanks to magic ECTAs, a fraction of the labor, we built something where you give an entire module, and it finds laws on them. So, showing you 2 domains, the Hectare domain and the spectacular property finding domain, where you set up an ECTA and hit run, and it solves it way better, faster than anything before. But there are more domains like that, and thankfully there are also more ecta words in the dictionary. So, if you have such a domain that you think might be amenable, set up ECTA, hit run, get something really fast. We're looking for collaborators, and maybe you'll be the person to create nectarine or delectable. But hopefully not rejectable. So I encourage you to check out the paper. There's a lot of cool stuff in there, especially a lot of details about how we make cycles work. It's very interesting. Yes, thank you, and I'll take questions. Now, as a little PS, so all the figures I've shown so far have just been drawings, and the top right, that is what an actual ECTA generated by a tool looks like. Thank you.